Hello everyone, my name is Ben Walker. I am a technical lead at Intel. My regular day job is as a core maintainer of the Storage Performance Development Kit, SPDK. Today I'm planning to talk to you all about TCP networking for storage software developers. So we'll focus specifically on ways to write network stacks for storage protocols. I'll be thinking mostly about NVMe-over fabrics and iSCSI and similar things. And I hope it's useful more broadly than just explaining what we've done in SPDK. I hope it's useful in your stacks back in whatever software application you have. So with that, I'll just flash the notices and disclaimers up for a moment. What are we going to talk about today? I feel like we have to start with some amount of level setting to get everybody to the same place. We'll talk about what makes storage networking unique, different from other kinds of networking. We'll talk a little bit about the basics of how to write a network stack and a protocol parser and things like that. And we'll cover blocking versus non-blocking operations and grouping connections. And that will get us all to the same level. I'm going to have to go very, very quickly through all of that, so it will not necessarily be enough detail for you to go off and write your own stack yourself, but I will do my best to get us all to the same place, and then we'll dive into what I'm calling the good stuff, the real meat of this talk. Better strategies for grouping connections and the options there, trade-offs between system calls and data copies, zero copy transmit, which is excellent, and we'll end on the new cool stuff that is often not yet deployed in production. Primarily talking about IOU ring. So let's get into it. So what does make networking storage networking specifically? For me, that means the protocol is probably modeling a fixed size ring over top of a TCP stream. In this ring are placed commands. The commands are usually small. I think NVMe-over fabrics is 72 bytes or something. And those commands describe operations to perform. Those operations then involve large amounts of data. And then the other really important thing is that in storage networking, connections are long-lived. This is actually quite different than most other things where the connection is established, like on a web server or something. For a short period of time, data is exchanged and then it disconnects. So in storage, the connections stick around. Okay, so a little bit of the basics of how you write a network stack, and we'll go very quickly here. Every operating system today we'll discuss, it's going to be primarily Linux, but every operating system we will discuss today represents a connection as what they call a socket. And it's interesting, the Berkeley Socket API, where this was first introduced, is from 1983. It's getting up there in the years. There are many OS-specific extensions to use sockets, and also the behavior within the POSIX standard is completely standardized, but across other operating systems that don't adhere to POSIX, like Windows, there's still a socket and the API is familiar, but the behavior is not exactly the same. There will be differences. But the basics are data is sent using the send system call and data is received using the receive system call, and you pass in the socket and a data buffer to both of those, and it attempts to do the send or the receive. A few key points though: the send call does not wait for the data to arrive at the other end of the connection. It is simply copying it into an OS buffer and returning immediately. And the only reason send would not work is if the OS buffer is full. Or if the connection is dropped, of course. Then for the receive call, it's important to note too that when you say to receive a certain amount of data, barring some flags which we'll discuss, the default behavior is to receive up to that number of bytes, not all of that number of bytes. And that's often because you don't necessarily know how much data is coming. Okay, so throughout this whole talk, we'll talk about a model server application that we can think about. We'll start off with the very simplest design from long ago, flashback to the late 90s. A simple server design would have been to spawn one thread per socket, so the server is accepting sockets on a listening socket. And every time a new one is detected, it spawns a thread, and that thread performs blocking send and receive operations on the socket. This is how the old Apache web server worked. So that's kind of how I think of it. It turns out that this model is very straightforward. It's easy to code, easy to think about, but it does not scale well. And the primary reason it does not scale well is as soon as you have, beyond a certain number of threads, then the threads are all contending with each other, swapping in and out, and it's just too difficult of a scheduling problem at that point to get the right things to run at the right time. There's just too much overhead in a thread swap, in a context switch, to make that run efficiently. But this model still is just fine for simple clients, where you probably have some number of threads, or maybe one thread that the client has created at the beginning of time, and those can perform blocking operations if they wish. So in order to do better than that model, we need to get rid of the thread swapping overhead. And that means we need to process many sockets from one thread. And so I'll think of this as the Nginx web server model, where it's multiplexing many sockets onto, in Nginx's case, a single thread. And to do that, we're going to need two important features from our network stack, or from our network APIs. One is we need some way to make send and receive operations not block, because if they block, then we can't go off and do something else. So we need them to attempt what we ask them to do, and if they can't right now because OS buffer's full or there's no data to receive right now, they need to not block, but instead just tell us, hey, I can't do that right now, and we'll try again later. So that way we can go off and work on another socket. And then we also need some way to efficiently group together the connections, because if you have a huge set of connections on one thread, 1,000, 10,000, something like that, you'll quickly see that we're just looping over the set of sockets, 10,000 or whatever we decided, and we are calling receive on every one of them to check if there's data there, and that has way too much overhead. So we'll get into that. All right, so I'll cover blocking versus non-blocking of those two first. Fortunately, sockets can be set into non-blocking mode. And what that means is they will not wait around when they can't process a request immediately. Instead, they will return eBusy or E again as an error code. Or they will partially complete the operation, whatever they can do. And there are many ways to control the blocking or non-blocking behavior of a socket. I've listed out the names of these things on Linux and FreeBSD. On Windows, you can do all of these things. They just have different names. So the socket can be globally switched from blocking to non-blocking mode. Blocking is the default way. So you can create a socket and then switch it at any point, one way or the other, using an F control. With the O non-block flag. The socket can also just be created in non-blocking mode. I don't actually think you can create the socket in non-blocking mode on Windows, but on Linux and FreeBSD, you can just right from the get-go be non-blocking. And then there's actually individual flags you can pass to receive and send to control just for that one request, do it one way or the other. And this is message wait all and message don't wait. So you have a lot of control over the exact behavior here, which is really, really convenient. So if we use non-blocking sockets and we think back to our model web server that we were thinking about, we would change it to now work in the following way. We would spawn one thread per core instead of one thread per connection. That's a big change. So there's many, many fewer threads. And then on each thread, we would loop over a set of sockets that have been assigned to that core. So as connections are being accepted, they're getting distributed to different threads, and we'll talk about algorithms for doing that as part of the talk later. But let's think of it as round robin. So they're being distributed to the different threads, and they're being held in like a linked list or something, or an array. And that thread is then looping over that set of sockets and is performing non-blocking send and receive calls. So if there's data that needs to be sent, it tries to send it, and if it fails, well, it just leaves it in our buffer and we try again later. Or if there's data that needs to be received, well, we don't know if there's data to be received or not, so we always try to receive, and it tells us did it find anything or not. And sometimes the answer is no, I didn't find anything. And so then we just try again on the next loop. And so this is better in some ways, but not all the ways. So there's no context switches here. You know, the number of threads we spawn is fixed. There's one thread per core, so there's no context switching going on at all here between different threads. We've eliminated that overhead entirely. But what we are doing is making a whole lot of system calls speculatively, you know, particularly receive. We're just receiving to try to ask if there's any data yet. And that's expensive. So this is maybe better. It's moving in the right direction, but it's not fixed. So the most important observation from this model we can make is that on any given loop through the set of sockets, most of the sockets are idle. There's nothing to receive. And that's just a function of the available network bandwidth. There's only so much data that can be received, assuming you're spinning here around, you know, your thread loop pretty quickly. There's just only so much data that can arrive. And so the set of sockets that actually needed to have a receive call done on them is very sparse. So now we'll get into the second half of the solution, which is better ways of grouping connections. The Berkeley Sockets API, way back, I don't think it was in the original 1983 API, but shortly after, defines a way to check for sockets that are ready on in a set. So you can build a set of sockets, call this poll system call is what it's called, and it will tell you which of the set are ready for you to call receive on, and you can skip the rest of them. And the way this poll call works is you basically build an array of poll FD structures which point at the socket and then have a scratch space for a flag that you're supposed to set to 0, I believe. And then you call poll with that array, and poll is going to, inside the operating system, loop over your array, check every socket, basically doing an internal receive, non-blocking receive. If the non-blocking receive, you know, of like 0 bytes or whatever, says, hey, there's data here ready, it sets the flag in the poll FD that you passed in, and then poll returns. And then your application loops over this poll FD array again, checking for which ones are set. For whichever ones are set, it calls receive. This is still doing the same amount of looping over the sets of connections as the other solution where we were just calling receive directly. The difference here is that we only made one system call. And it's the system call transition that's particularly expensive. You know, the CPU has to drop to a higher privilege ring, and to do that must clear a bunch of register state, and that's expensive. It's much more expensive than a regular function call. So you're eliminating a lot of overhead in the you know, kernel to user context switches by doing this, but it's still fundamentally looping over the set of sockets every time. Okay, so it would be nice if we could do better than that, especially as we scale the number of connections very large. So POSIX doesn't have a better way to do it, but both Linux and FreeBSD, at least, have better ways to do things like this. Windows has I/O completion ports and overlapped I/O and other complexity. Works quite a bit differently. We're not going to have a chance to talk through all of that, but it sort of serves the same purpose. Okay, but for epoll and kqueue, they don't work exactly the same way, but for the level that this talk is at, we can mostly treat them as the same thing. for these, the set of sockets is not passed into the system call that queries whether they're ready, but instead we create the set ahead of time. We're going to create an epoll group. It's a separate system call, and at any time we can add or remove sockets from that set, and the kernel knows the set exists. It's there and it's ready. And so what that means is anytime a network event happens, like there's an interrupt and packets arrive and they get processed through the TCP stack and appended to the TCP stream that's pending for that socket, the kernel can just go say like, hey, is this socket that I just got packets for associated with any of these groupings? And if it is, it just makes a note of that in some efficient way on the grouping. And note that that operation is O1. It's not looping over anything. It just says, I got a packet for this connection. This connection points that is in this set of groups, usually one, and it marks that group as saying, hey, this socket is ready. And then later, when the application comes in and checks, checks the set for which ones, which sockets have data waiting to be received or are ready for a send operation, it already knows the answer. It's already been marked on that grouping, and it could just return very quickly and just tell you, like, here's the set. So this is wildly better. So if we revise our non-blocking server to then also do this efficient grouping, we similarly spawn one thread per core, just like before. And on each thread, we're going to distribute the connections. But instead of holding them in like a linked list or an array, we're going to put them into an epoll group or a kqueue using the kernel APIs. And then our thread is going to loop, asking the epoll or kqueue object which ones are ready, on each iteration, which is efficient. And so now we're finally at a place where this is much better. We are not iterating over the set of sockets every time. We're only touching the busy ones. This is how most server software, TCP-based server software works. And so I would say this is considered state of the art. And so now we have made it through the level setting. All right, now we can get to the good stuff that I really wanted to talk about. We've all sort of gotten ourselves to a place where we understand what most software looks like. It's an epoll group with one thread per core or something like that. And it's looping through, asking the epoll group which connections are ready, and it's performing operations just on those. But now the question is, how can we do better than the quote-unquote state of the art? And that's what we'll spend our time on from here on out. So I said connections get assigned to threads in some way, and I mentioned round robin. That's kind of the normal way to do it. Let's think about that for a minute. How should we really be doing that assignment? Round robin it is kind of the norm. It's simple. You just loop through every time a connection goes, you send it to the next thread, and then you just loop around. You might think that it would be better to distribute the connections instead based on activity. And this is a completely reasonable thought. The connections, say you have 4 threads and 4,000 connections, and there's 1,000 on each thread. You may have like 2 or 3 connections which are completely eating up all of your bandwidth. And they're the only ones that are active right now at any given time. And what happens if, round robin, they could all have been assigned to one thread? It's not particularly good. So distributing them based on activity is sometimes an improvement. The problem is when you need to make this decision, the connections are often not active yet, and you have no idea. And also the activity levels of the socket vary wildly over time, right? Like sometimes people are using their connection, especially in storage, like they're reading from the disk at this moment in time. Their connection's busy, and then they stop, and then they do it again later. And so it's really, really spiky. And so you often can't do the rebalancing or the redistribution of the sockets to the threads fast enough to matter. So really in practice, distributing based on activity, unless you have like extra information somehow in your application about what the behavior, the patterns are going to be, is actually not worth doing. It never really works out. But is there another way we should do it, or other considerations? Should we think about what the hardware is doing? And the answer is definitely yes. So a little bit about how a NIC works. NICs place packets into what they call RX queues. Receive queues, the NIC people call them RX queues. I'll use the networking person terminology. The NICs have a bunch of these RX queues, and they drop packets into those as they arrive. And so the NIC has different ways in hardware to select which RX queue to dump a packet into. So the naive way, maybe the old way that NICs used to do this, is they would just round robin across the RX queues as packets arrived. Doesn't matter, no information. They just spread them out. And this is good in some ways. It makes sure like all of the CPU cores on the host system are engaged in processing the packets. That's great. The more modern way is to do some sort of algorithm based on the four tuple. The four tuple is the source IP import and the destination IP import. And there's other ways to do this as well. But what they end up doing is they have different algorithms for keeping all of the packets for a single logical connection on the same RX queue. And the reason that's important is because there's shared state within one connection. And so if they dump them all to one RX queue, there's optimizations in the software stack that they can make and cache locality benefits. So that's all great. That's mostly what NICs are doing today, is they keep a connection onto a single RX queue. But then let's imagine that a packet arrives on core 0 for a connection, and our application has no idea which RX queue got selected for our connection. So on a thread that happens to be running on core 1, we then call receive. And we say, I want the data for this socket. What this means is now that the networking stack has to do some sort of coordination between core 0 and core 1. Core 0 may be putting new things onto that TCP stream, and core 1 is taking things off. And so they have to be coordinated. It turns out this is a major performance problem. We see this in traces, locking and message passing in the network stack. It mostly manifests as latency outliers in particular, when we have to do a message pass and something has to wait for a lock or something like that. We see spikes in our latency profiles, P99 latency and things like that. So one observation is, if we had just known which RX queue our connection was on, we could call receive from only the core that RX queue is getting processed on. And then it doesn't have to do, there's never any lock contention, we're on the same core. And things are really fast. And it eliminates these latency outliers. So the real question is, can we align our groupings of sockets so that they all use all the sockets in the group happen to use the same RX queue? And the answer is yes, we can. There's a couple of ways to do this. Some NICs, and these are all very new NICs, give hints about their internal RX topology via the socket APIs. So the get sockopt system call can be used with two different flags. One is SO incoming CPU, and the documentation is not entirely clear about exactly what this means, but I know in practice on several NICs, what this means is it's the most recently associated CPU core for the RX queue. And so if you call this on a newly established socket, it will tell you what RxQ it's assigned to, effectively. And you can then use this to group together all of the sockets where their packets are landing on the same RxQ or the same CPU core, and then attempt to use them from that core. There's also SO incoming NAPI ID, which works on at least Intel E800 NICs, where it is telling you what they call the NAPI ID, but that is like literally one-to-one map to the RxQ. Like they are just telling you an identifier for the RxQ. It doesn't actually have any meaning. The number doesn't mean anything in terms of which RxQ it is on the NIC. You can't like map it to this specific one using this API. But every unique NAPI ID is a unique RxQ, and so you can just group them by NAPI ID. And if you use all of the, if a particular NAPI ID is only used from a single thread, then there's never any contention in the network stack. So those are the really server-side APIs where we're accepting a connection, and we need to figure out what RxQ is that connection associated with. Those are the two methods you would use. Then you can also tell the NIC, at least on Intel E800 NICs, you can tell the NIC which RxQ to use, which is a little bit of a reversal. The only catch is you have to do this before you connect the socket, because in order for the socket to be connected, it has to know what RxQ to use to receive packets on. So you can create a socket object, do this get set sock opt with SO mark, and basically give it a number. It doesn't really matter what number, it's the uniqueness of the numbers that matters. And it will pick an RxQ for that particular number, and then any other socket you set to that same number will share the same RxQ. So this is useful on the client side, where you're the one creating the connection initially, and so you have this opportunity to pick. So if your client has like 4 threads or something, you can pick a number for each thread that's different and mark the sockets that are created on that thread and then use them only from that thread, and there will be no contention. Interesting fact, this SO mark mode was added specifically to implement NVMe-oF fabrics initiators in user space for SPDK. Obviously, we believe it to be much more broadly useful, but this is like literally a storage thing. Storage is driving the networking in this particular case. All right, now I want to switch gears a little bit and talk about some of the complexity in making system calls and some of the alternatives to making so many system calls. For any given storage protocol, the kinds that I'm envisioning, iSCSI, NVMe-oF fabrics, they all kind of work the same way, where you have this muxing of a ring of fixed size commands and interleaved data payloads in between them, and scatter-gatherless also. And so in order to figure out what's happening, you have to first receive the first command. The first thing will always be a command. And we'll imagine it's like 64 bytes. Look at what it says. What kind of command is it? And then it'll tell you, like, am I followed by an SGL? Am I followed by data? Or am I done? And if it's followed by data, you have to receive however much data it said, came from the data. That would be like, if it was a write command, it would have like in-capsule data. Or if it's a response to a, like a R2T command that the target sent to the initiator is going to respond to that with a bunch of data, command followed by a bunch of data as requested. You have to look at how much data is following you. And it could also be followed by an SGL. It sort of depends on the protocol and how it's working. So, and then you repeat. So you end up, if you were to make a receive call for only the amount of data you knew should be there, for instance, the first thing you know is you're going to get a 64-byte receive. So if you attempt to receive 64 bytes, and then you say it has a 4K SG or 4K data buffer after it, so then you receive 4K, and then you receive 64 bytes, and then maybe it says, oh, I'm just telling you, some control message, and then the next thing is 64 bytes. So you receive 64 bytes. You're doing a lot of receive of very small amounts of data over and over and over again. And this has a lot of overhead. But this is the way storage protocols typically work. So system calls, as I've said earlier in the talk, are very, very expensive, and you should generally avoid them. System calls also have mostly fixed overhead. It's in the clearing of the state and switching the security context. So they can't really be made faster. You know, it's a hardware change to make them faster. And so they have actually trended faster over the most recent couple of generations here. But they're always going to have fixed overhead. But then we can observe that we could avoid making some system calls by speculatively attempting to receive much more than may arrive. And remember, at the very beginning, I said that receive will receive up to the amount we requested, but not necessarily all that we requested. It'll just give us the data once we've hit the low watermark, which is by default 1 byte. So this is a great strategy. We can just try to receive a big chunk, and then the kernel just gives us whatever it has, and we can parse out of that without making additional system calls. And we can walk through the 64-byte commands and the data buffers out of there. The problem then we run into is one of lifetimes of the data. So the commands, obviously, we pull off the socket and we parse immediately, and we can throw them away, you know, or copy them somewhere. They're small, they don't matter. The data buffers, we are going to have to DMA to a disk or something in the back end, you know, or send out on the network, something like that. So they have to live until that back end operation is finished, and it's asynchronous, and it may take a long time. So typically, you have to then copy the data out of the speculative buffer that you received into a pool of long-lived DMA buffers so that they can be transferred elsewhere and have the right lifetime. It may be possible to architect your network stack in some way where you can have a very large pool of buffers go right to the network stack, and then they can live a long time until those backend operations are done. I think that's, you know, an excellent approach. It's quite difficult and goes up and down your entire stack, so it's not the way most software works. Most software does a speculative receive and then copies. This copy is expensive, but there's some point where that copy is cheaper than making all the extra system calls. And we've done a lot of benchmarking and measurements on this, and at least on current generation platforms, it completely depends on the platform. But at least on current generation server platforms, you know, Intel Xeon SP, we see that point at about 8K. So try to receive 8K always, and then copy. And so as you do this, you know, if you definitely know as you parse the protocol that the next 64K or whatever is data, you can skip buffering it through that 8K, you know, speculative receive and just go straight to your DMA buffer. That's a great optimization. You know, we do that in SPDK. But when you don't know what is next, it's best to speculative receive 8K, at least on these platforms, and then parse and copy, which is, I think, really interesting. You know, that's probably larger than most people would have expected. But generally speaking, copying is relatively fast compared to the system call overhead. Okay, so coming around to the end here, we'll talk about zero copy transmit next, and we'll close out with IOU ring. So zero copy transmit depends on a couple of cool hardware features. One in particular is called TCP segmentation offload. And so when you do a send, the data is copied into an OS buffer and the send returns. And without hardware offload, without TCP segmentation offload, TSO, the kernel would then take the data that you posted into that buffer, and it would packetize it. It splits it into MTU size packets. It would generate TCP, IP, Ethernet headers, checksums, and then it would post those packets to the TX queue, the transmit queue of the NIC, which would DMA them and send them on the wire. Modern NICs almost universally have a hardware offload for this packetization step, which is called TSO. And so the kernel can simply post the user data buffer as it was, maybe it's a megabyte or something, to the NIC, and the NIC will break it up into 1500 byte packets and insert the headers and generate the checksums as it sends. So the OS doesn't have to do that anymore. The OS does have to hold the data buffer around until the ACK is received for all of it, because it needs to support retransmits. But no longer is the kernel actually touching your data buffer. Okay, so what zero copy transmit does is it observes that the data buffer is not being manipulated or modified by the operating system anymore. It's not being copied by the operating system anymore. It's just being posted to a NIC as is for DMA. So fairly recently, I think in 4.18 of Linux, they added a new flag to send called message zero copy. And if you say message zero copy and you do a send, it will not copy your data into the OS buffer. It will simply put a placeholder into the send queue in the OS that points at your user buffer. And then it's up to your application to not change that data buffer while it's still sending. And sometime later, via a new mechanism on receive, they will tell you when they are done sending the data, and then your application can go release that buffer or reuse it for something else, which is pretty slick. So it DMAs directly out of user space. In order to make this work, the OS must pin your data buffers. They have to have physical addresses that are consistent. The mappings from virtual to physical cannot change. This pinning step does have overhead. We find that zero copy, the original guidance on zero copy use in the kernel documentation says send at least 10K for this to make sense. We actually find that it's better than that. We find that it is at least breaking even at 4K, and it is better at anything larger than that. For sending, quite considerably better the larger the send is. So if you can batch your sends up, the bigger the better. It gets very good. Because we're storage, the smallest amount that we typically send, of data at least, is 4K. So perfect. We don't have to have cutover points where zero copies on or off, etc. We just turn it on. It's always on. It's always good for us. So then some people ask, why is there no zero copy receive, right? And the answer is really that it's hard, and nobody's made it work, suitably yet. The operating system drivers to do this must keep data buffers posted to the NIC, or the NIC will be forced to drop incoming packets. It has nowhere to DMA them to, and it can only buffer so much. It has tiny little, memory buffers. The packets are often small and scattered as they arrive, and they arrive out of order. And so you can't just DMA to the user buffer because, one, it may not have been posted, like the user may not be actively trying to do a receive. Two, the packets may not, be in the right order, and you have to hold them somewhere. And three, they may not have arrived in the right order, so you have to tell the user, you have to give the user a scatter gather list back of where their data is. And then there's also protected information in the packets, like the MAC addresses and things like that, that you're not supposed to see, without privilege, that have to be stripped and parsed. So if you DMA directly to a user buffer, it has the headers still on it. So you have to strip those. I think this is probably technically possible for somebody to figure out how to do this. The APIs would look very different than receive, I think. In fact, I think it has to be an asynchronous receive, much like the send became async. But so far, this has proven to be mostly an intractable problem. There's no good solution here. I do want to mention that Linux does have some limited support If you are able to control the minimum transfer unit on your network, like you're in a data center and you're in full control of all the switches and everything, and you can set the MTU size to a multiple of the page size on your operating system, then Linux does have a way for it to like allocate, header space for the headers followed by a 4K data page. And when data arrives, it will just DMA there, and then you can mmap the socket, and it will show you just the data page part without copying. There's overhead in the mapping, but especially if you can do like MTU sizes of 64K or something, and you're doing, giant block or object movement, this can be quite useful. That's really what it's for. But it's very difficult to use that generally. You can only use it on private networks effectively. Okay, and then we'll close it out with some discussion of the future and where things are going with network stacks. Things are really, really changing, pretty dramatically in how software is going to be written to use networking, I believe, over the next couple of years. We've been at IOU Ring for about 2 years now, maybe 3, and it has matured a lot, and it is completely usable, but it could... it still will take time to get this deployed in production and all of the corner case behaviors worked out for this to become commonplace. So the key features of IOU Ring is it lets you do asynchronous send and receive. You post a send to the kernel, it tells you when it's done. You post a receive to the kernel, it tells you when it's partially done. It also allows you to batch system calls. IOU Ring works kind of like NVMe for my audience here at the Storage Developer Conference, where you post a bunch of descriptors to a ring, and then you ring a doorbell effectively and say, go process these. But all the descriptors can be for different file descriptors, like different sockets and different operations. So, and only the ringing the doorbell part, quote unquote, is a system call. So you can batch arbitrary numbers of system calls together and make one actual system call, which is fantastic. It also has mechanisms to reduce the overhead of operations on file descriptors by pre-registering the file descriptor with the IOU ring, and this just reduces the amount of overhead in validating that it's still live and okay to access every time you do a send or receive to it. So it drops the overhead down. It's quite nice. It also provides, since it's naturally asynchronous, they've added support very recently for zero copy send on a socket through IOU ring that works. It doesn't have like this send call that normally is complete. When it says it's complete, your buffer is free. Now it's not. It changes all the rules like I described before with zero copy. Now it just sort of works like a regular send in IOU ring. It's an async send, and it tells you when it's done. And it's much nicer. And it also allows this really interesting feature of pre-posting receive buffers to the IOU ring, so that you can basically post it a pool of memory and then post a bunch of asynchronous receives. And when the receives finish, they'll pick or are ready to receive data. The kernel will pick one of the buffers from the pool, fill it out, and then complete your receive and tell you which buffer it put the data in. This is so that you can post like 10,000 asynchronous receives to sockets, but you don't have to post 10,000 buffers. You can post 100 or something, right? Lets you save memory. All right, so I'll talk a little bit about system call batching, which is just one of the most powerful parts of IOU ring. You drop multiple descriptors into the ring. You then do one single system call. So if we look back to our epoll case, which was the ideal case we got to before, you would do one system call to check the set, and then you would do n system calls where n is the number of sockets that are ready to be processed. And now what you do is you build up a whole bunch of descriptors into the ring, whether they're sends or receives or anything like that, and then you do one system call. And it's one system call all the time. That's it. That's the most you can ever need, is one system call. It's not dependent on the number of active connections. So we've dropped from 1 plus n or n plus 1 to 1 per loop. and so it's fantastic. This drops overhead considerably. You know, as long as your stack can be written to deal with asynchronous operations everywhere. So there's a couple of challenges with IOU ring that I think we're still working through. There's been patches out of the mailing list within the last year on some of these things. There's a couple of weird corner case behaviors that are still maturing. For instance, you can still use the message wait all flag in receive or in send. And so when an IOU ring does that, using that flag ever result in a partial send? I would think never, and I think you would want to be able to post an asynchronous send and say, I don't want you to complete this until it really sends. You know, because you don't need to know about a partial send if it's async already. But there are cases where people are still reporting partial sends, and so we need to work through some of that. Maybe by the time this talk airs, it's already worked through. I don't know. That's an active discussion. The other reason being able to avoid partial sends is really important for IOU ring is if you do an asynchronous send, the TCP stream has to stay in order. So if you do two sends, post two sends to the same socket, you need to know that the first one finished before the second one ran. And so that ordering is critical. And so if the first one completes partially, but then the second one works, now you've corrupted your TCP stream. So these sort of flags are really, really critical, and they have to work 100%. The other big one is you've got to rework your software to do all asynchronous operations. Not so big a deal for projects like SPDK, which are all async to begin with, and are kind of working around the fact that the other ones are like non-blocking style instead of async. But for a lot of projects, that's quite difficult. And then the remaining major problem in networking for storage is there's still a data copy from on the receive side between the kernel RxQ packets, the Ethernet frames that have arrived, and the user buffer that we're receiving into. And this has been there since the beginning of time. It's still there with IOU ring, and it is probably the top performance challenge in all of TCP, especially for storage where we're moving lots of data. So there's no line of sight currently on fixing that. Okay, I think we've gone through everything that I'm going to get to within the time allotted. So I really am thrilled that I got to do the virtual talk. I was so disappointed that I couldn't be at SDC in person this year. Thank you very much